21st International Physics Olympiad, 1990. IPHO. I offer private tutoring for preparation for physics Olympiads. I currently have openings. Write to me if you are interested. There is a discount for group lessons. My email is fred1996@hotmail.com. Problem 1. X-ray diffraction from a crystal. The solution to this problem can be found at the link in the description under this video. We wish to study X-ray diffraction by a cubic crystal lattice. To do this, we start with the diffraction of a plane, monochromatic wave that falls perpendicularly on a two-dimensional grid that consists of N1 by N2 slits with separations D1 and D2. The diffraction pattern is observed on a screen at a distance L from the grid. The screen is parallel to the grid and L is much larger than D1 and D2. Question A. Determine the positions and widths of the principal maximum on the screen. The width is defined as the distance between the minima on either side of the maxima. We consider now a cubic crystal, with lattice spacing, A, and size N0, A, by N0, A, by N1, A. N1 is much smaller than N0. The crystal is placed in a parallel X-ray beam along the z-axis at an angle theta, see Figure 1. The diffraction pattern is again observed on a screen at a great distance from the crystal. Figure 1. Diffraction of a parallel X-ray beam along the z-axis. The angle between the crystal and the y-axis is theta. Question B. Calculate the position and width of the maxima as a function of the angle theta, for small theta. What in particular are the consequences of the fact that N1 much less than N0? The diffraction pattern can also be derived by means of Bragg's theory, in which it is assumed that the X-rays are reflected from atomic planes in the lattice. The diffraction pattern then arises from interference of these reflected rays with each other. Question C. Show that this so-called Bragg reflection yields the same conditions for the maxima as those that you found in question B. In some measurements the so-called powder method is employed. A beam of X-rays is scattered by a powder of very many, small crystals. Of course the sizes of the crystals are much larger than the lattice spacing, A. Scattering of X-rays of wavelength 0.15 nanometers by potassium chloride, which has a cubic lattice, see Figure 2, results in the production of concentric dark circles on a photographic plate. The distance between the crystals and the plate is 0.10 meters, and the radius of the smallest circle is 0.053 meters, see Figure 3. K+ and Cl- ions have almost the same size, and they may be treated as identical scattering centers. Figure 2. The cubic lattice of potassium chloride in which the K+ and Cl- ions have almost the same size. Figure 3. Scattering of X-rays by a powder of KCl crystals results in the production of concentric dark circles on a photographic plate. Question D. Calculate the distance between two neighboring K ions in the crystal.